Hello, and welcome back to Shiksha DaCosta. Today we're going to learn how to collect exponential data. This is actually part of the second half of the unit of exponential functions, and in this unit you're going to learn to identify and represent an exponential function and solve problems that involve exponential functions, especially those that come from the real world. And so we're going to be focusing on this specific success criteria today. Today, specifically, we're going to learn about exponential functions that come up from the real world. We're going to learn how to collect and graph the data that they create and how to create an equation of a curve that best fits that data. Specifically, we're going to collect data that can be modeled as an exponential function. We'll do that in an investigation using technology and just by hand. We'll collect data from primary sources and from secondary sources. To start off, I'd like you to give this experiment a try. So all you'll need are 10 coins, or even if you have one coin, you can flip it 10 times and record that as sort of one event. Once you're done flipping all the coins, you'll only flip the coins again if they were heads. So you're going to remove any coins that flipped into tails, record how many coins are remaining, and then flip the remaining coins again and again until there are no coins remaining. You're going to record all of that data on a chart, and then you're going to graph that data, and then repeat that entire experiment 2 more times. So here we go. That we are starting with a group of 10 units. A group of 10 coins, and once we flip them all, now we've got 1, 2, 3, 4, 5, just 6 remaining. When we flip only the remaining ones, now I only have 2 remaining. I'm going to write that down. When I flip those 2, both turned up heads again, so that's still 2 remaining. Now there's only 1 remaining, and when I flip that one, there we go. So now there's none left. So these are how many coins were remaining after these many flips. We're going to plot that data on a graph real quick, and then move to flipping all the coins back to heads and trying this one again. 1, 2, 3, 4, 5, 6, 7 coins remaining. Now just 2 coins remaining. 1 coin remaining. And finally, none. So this time it only took 4 flips to get down to 0. And let's plot that on my graph right there. And then in trial 3, let's start back up at 10. 1, 2, 3, 4, 5, 6 remaining. Just 2. Just 1. Oh, still 1 remaining. That guy just refuses to die. And finally, none left. All right, so this would be the data for this experiment. And what we're going to learn today is that, if you're looking at these 3 graphs, you might notice that, hey, they kind of seem like they go down very quickly at the start, and then they sort of slow down their decrease, very similar to an exponential curve, just like this. And today we're going to learn not only how data comes up that appears that will, or what situations in real life create exponential data that creates a curve like this, but how do we actually create this curve that fits the data really well, and how do we come up with the equation for it? One of the places in real life that you'll see exponential data come up a lot is something called inflation. Inflation is a word that describes how things cost more and more over time. For example, in the year 2000, maybe you went out and you went to a lovely bakery to buy a cupcake and it was there for $1. Well, in 2025, that very same cupcake would cost something more closer to $2.04. So that is just a sort of an idea of how much that cupcake has increased in price over time. What I'd like you to do right now is go ahead and scan this link here. And that'll show you inflation data for 25 years in Ontario, the first quarter century of the 3rd millennium, I guess. When you go to that link, you should see the inflation data pop up here. And this is a spreadsheet. It's using Google Sheets to collate it. And over here in the spreadsheet, you've got a bunch of dates. So this is January 1st, 2000, February 1st, 2000, and so on. And this is the cost of food in that year. So you can imagine this as being, for example, one cupcake. That same cupcake that cost $1 on January 1st might cost $1.02 on June 1st. You can use this drop-down list to choose a different sector if you would like. I'm going to analyze food as part of this lesson, but certainly you can analyze any of the sectors that are available to you here. Once you're done picking the right one, what you can do is select the first two columns, just like that. And once you're done that, you can click on Insert and then Chart. And when you do that, something like this should pop up. So for me, it said food versus date, and it created a wonderful graph for me. And you can usually choose what type of chart you would like to create. And looking at this chart, I can see that the price of food in the year 2000, anything that cost $1 increased in price until the end of the year 2024. So the start of the year 2025, it had gone up to just above $2. And if I examine this graph a little bit more closely, I can almost imagine that there's sort of like a curve. If I wanted to make it exponential, that might sort of look something like this, right? The graph seems to be going a little bit flatter on this side, and then it picks up speed quite quickly until it looks like it's rising a little bit sharper closer towards the end. That situation and other situations like repeated probability experiments, population growth, all of those are exponentially related situations. And you can generate your own data using an experiment like that, or if you look for a secondary source that you trust, you can always find data from there, like, for example, Stats Canada. Once you have your data, if you make it into a graph, and if that graph appears to be exponential, if it seems like it's making that nice curve, you can find out what is the equation of the curve that best fits the data using a technique called regression. And for example, if I were to use the web graphing calculator Desmos, I can put in a bunch of data, and then if I add another expression and I add this very specific expression, notice this looks a lot like y equals a times b to the power of x. Y1 and x1 are the number one is in here to tell Desmos basically that I'm referring to x1 and y1 from my table of values. And this symbol here, not equals, but it's called the tilde sign. This symbol is telling Desmos, okay, I don't actually know the equation. I want you to tell it to me using regression. And Desmos will do that. So it'll create a curve on your graph. These orange dots are coming directly from my table of values. The blue curve is coming from the regression expression that I've put in. And not only does it plot out the curve that fits the dots really well, it actually also tells me what the equation of this curve is. It's telling me, because I put in A and B here and I didn't tell Desmos what A and B the values actually are, it will do that for me. It's telling me, hey buddy, A should be about 32.1626 and B should be about 0.501699. And that kind of makes sense with what I know about exponential functions already. Notice the starting point was about 32.1, and that's really, really close to that. And then every time x increased by 1, the y values seem to be about half of what they used to be. 16 is half of 32. 8 is half of 16, then 4, then 2, then 1, then half, then a quarter, then an eighth. And so it's telling me what the a and b values are, and therefore the actual equation for this blue curve is f of x is equal to a times b to the power of x. In this example, I'm going to take a look at that inflation data. So according to this data, inflation caused food prices to double in 25 years from $1 just above $2. However, there were some years that were really bad. For example, in just this 1 year in 2022, which is just around the COVID-19 pandemic, food prices shot up by 15%. And now if this continued at that rate, continued going up 15% every year, how much would food cost in 2050? Would it double again from $2 to $4? Or would it go up even faster than that? Let's take a look. I made a table of values here, and I'd like you to try to pause the video here and fill this in. In this table of values, we're trying to measure T years in a very specific year. So T years after 2025, what was the cost of food at that time? So in 2026, in 2025, it was $2.04. And we're saying if it increased by 15%, what would it be the next year? And the way you increase a number by 15% is you can take that number and multiply it by 1 plus whatever that percentage rate is, but you have to change it into a decimal. So for example, if I want to increase it by 15%, I multiply it by 1 plus 0.15. That's 15% as a decimal. You just divide it by 100. And 1 plus that is 1.15. So if I take this number and I multiply it by 1.15, I will increase it by 15%. So that same cupcake that might have cost $2.04 in 2025 is going to cost $2.35 in 2026. And I can estimate that, in the year 2027, based off this 25-year data, or based off this idea that it would increase by another 15%, it might go up to $2.70 in the year 2027. So you can see already it's jumping up by about 31 cents, by about 36 cents here. And so if I want to find out for another year that's T years after 2025, I know that I'll have to multiply by 1.15 once, twice, no, T times, again and again and again, until I find out what is that cost going to be T years later, okay? Because I'm repeatedly multiplying by this number to move down the chart, it'll be T years later. So for example, in the year 2050, that is 25 years after 2025. And so I know I started at $2.04. I'll have to multiply by 1.15, so that food cost will increase by 15%, not just once, not just twice, but 25 times. And that means that same cupcake that cost $2 in 2025 will, my estimate, if food prices keep going up by that much every year, will cost $67.15. And this is a good illustration of exactly why a inflation rate that's extremely high is such a bad sign for the economy. An inflation rate that's that high will mean that things will go up in cost so quickly that people will not be able to afford that anymore. And 2022 really was a tough year in that regard, not just because of what happened that year, but because everyone who's working in the economy knew that if they couldn't get this under control, if they could not get this number down back to around 2 or 3%, costs were going to just blow up and get out of control. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.